Hey, all right, students. I got a question on this real hard one here. I think this is the hardest one, but let's see if it kind of makes logical sense here. We have a child, and it's 40 kilograms in a roller coaster, and it is traveling in a loop of radius 7 meters. So I'm going to put 7 meters down in the picture. And I thought I printed it because step one, remember, is get a good physical picture of what's going on. And so often they have pictures. Pictures help understand what's going on, but other times they just give you words and you got to kind of doodle your own picture. But I found this best to just kind of print this up. There's this 30-degree angle. We'll talk about that. It says at point A, the speed is 10 meters per second. Okay. And at point B, the speed has increased a little bit. Kind of makes sense. It's going downhill a little bit. Assume the child is not holding on and does not wear a seatbelt. Okay, now I think the intent here is to say that there are no other forces other than just the child's bottom touching the seat. And therefore, the seat could put a force, but you don't have anything from your hand. You don't have a seatbelt on you. Obviously not a realistic problem. You can't ride a roller coaster without a seatbelt on. But I think they're trying to imply that really the only touching force, and I should say there's also gravitational force, but the only touching force is the normal one. In fact, I've gone a little too far because I'm already now getting into step 2 and drawing the free body diagram. But let me just kind of keep going and, get a good physical picture. And I think the good physical picture right here, assume that the child is not holding on and does not wear a seatbelt. This is the physical picture of, okay, then the only thing in the roller coaster pushing on the child is the bottom of the seat. And there's no sideways forces. Even then, we'll just say it's a minor amount of friction on the rider's bottom, but the left and right, there is none of that because the child's not holding on and then pushing them in or any other kind of forces because there's no strap, there's no seatbelt. So that's the physical picture they want you to have. And then it says, what is the force that the car seat puts on the child at point A? And then B, what is the force that the car seat puts on the child at point B? And then C, what is the minimum speed required to keep the child in the seat at point A? Okay, so I got a good idea of the questions, but let's keep going here because I would say the next big thing to do is to draw a free body diagram. And there's 2 different locations, and let's start at point A. So for problem A, we're at point A. I'll put a little circle for the child. And remember then the forces would be the gravitational force and, oops, my bad, everything touching it, which would be the normal force. So they're both pushing in the same direction. I almost drew up because, normally you think of a seat, pushing up on somebody. But I need to go back to my physical picture. And my physical picture says, okay, the roller coaster goes around. And so the roller coaster's upside down. So interesting here that the seat is pushing down and so is the gravitational force. All right. Now we can go on to step 3, which is to add up all the forces. And maybe, like we've done in so many, I'll put an X and I'll put a Y. And I'll say, look, the sum of all the forces in the X direction equals mass times acceleration in the X direction. And the sum of all the forces in the Y direction equal mass times acceleration in the Y direction. And so if you've been watching these videos, you know that what I always say is when we get to step 3 and we say, hey, let's write out the equations, to determine what is X and Y, we need a grid. And I'm going to do it in green here. But then a good choice of a grid is to make sure one of your axes is along the direction of the acceleration. And given that it's going in a circle, we know that the acceleration is v squared over r and towards the center of the circle. So that means a grid that is kind of the traditional grid, X being horizontal and Y being vertical, and I'll even call up positive, this would say then that the acceleration in the center of the circle, maybe I'll put a little mark down here and put a C for center of circle. I know that the acceleration then should be towards the center of the circle. That means right here in this math, when I add up all the forces in the y direction, I would get m times a negative v squared over r. And they use a capital R or a lowercase. I guess in the picture they don't give me any symbol. How about the problem? All right, so I'm just going to use a lowercase r. Okay, so there is the acceleration in the negative y direction. And over here, then, would be an acceleration of 0. It's not, well, I don't even think we need any of that. But I guess this would be a push on the left and right. So it might be gaining speed or losing speed. But if it's only under the effect of gravity, then it would, and if we ignore friction, there would be no acceleration in the x direction. And in fact, based on their description for the child, there is no left or right. So when you add up all the forces, which are none, you set it equal to no acceleration. And technically that's true, but doesn't really help us with anything in the problem. Now, the y direction's a little more interesting because one force is down, that's the weight, and the other force is down. And of course, those two negatives and then this negative would all cancel out, which is why we could have called down positive and these would have all come out to be positive. So what that means then is the normal force would be mv squared over r, and then move this to the other side, minus mg. Put another way, if you weren't going in a circle, this one would be gone, right? And the normal force would be down. And you would just have this negative mg here. But here, you are saying here that, if I can say this right, is for this one, we can figure out then what this value is, because they tell us that the child then is 40 kilograms. At point A, it's going 10 meters per second, and the radius is 7. Then if we subtract off 40 times 9.8, we can get this first part that says what is the force at the car seat. All right, so I will go 40 times 10 squared divided by 7. And that is 571 newtons, minus 40 times 9.8 is 392 newtons. And so taking that answer and subtracting that answer, I get a difference of about 179. So this child at this point is going to be okay because it's pushing downward, or put another way, if the child was not in the roller coaster, the child would probably make a parabola path like that, and it would have a radius or an arc bigger than the radius of the circle, so the roller coaster twists and really keeps the child in the seat. Or put another way, on its own, with normal force 0, this would be the path of the child, and we are trying to turn more than the natural parabola, so we've got to have an additional force on the child, and that comes from the bottom of the seat. So there is an amount of force of 178 newtons. Now, I'm kind of thinking maybe I should jump to C, because I noticed that C said something about point A again. So as long as I've done the arithmetic and the free body diagram for point C, let me put that in mind. It says, what is the minimum speed required to keep the child in? And you can kind of see, I kind of alluded to it, if the child was going slow, its natural path would be this. And it would fall out of the roller coaster because the roller coaster is making this path. And so the key to making this loop without needing a seatbelt, or if it was like a stunt car going around a loop, or a skateboard rider in one of these tunnels, or a motorcycle in one of those what do they call it, a ball of death or suicide ball or something like that, where they put a motorcycle in going around and then a second one, crazy. But you got to be going fast enough, and fast enough means basically that your natural path due to gravity, due to a projectile, would be greater than the radius, so that means it turns faster and keeps you hugging up against the sidewalls here. So there is some minimum speed, and apparently, you can see here, we're making it fine, so this speed of 10 meters per second is greater than the minimum speed. And you can see in the math that as the speed goes down, of course the weight staying the same, the normal force goes down. And eventually, if your speed gets low enough, your speed is equal to this. In other words, the normal force is zero. And at that point, you're turning naturally at the same rate that the roller coaster is turning. There's no interaction. And if you were to go even slower than that, you can see that the math says you have to have a negative normal force. In other words, if you're going too slow, you would actually have to have a seatbelt pulling you upward. The opposite of what, we said the normal force was down, in order to hold you on. Because again, your natural path, you're going so slow, is at a turn of smaller radius than the roller coaster. And you'd fall out unless you had some kind of negative value. And in this problem, we can't have a negative value because we don't have a seatbelt and we're not holding on. In a real roller coaster, that's possible, and we'd call that a negative force or a negative G-force on it. But what I'm getting at is all of these fancy words, if you kind of reason out the mathematics here, is a nice way of saying set the normal force equal to 0. So when the normal force is equals to 0, which of course coming back up here in this equation means when mg equals to mv squared over r, canceling off an m, which is kind of nice because then the speed's the same for every mass, and so this could be a big person or a small person. But if you take r times g and then take the square root, you're going to get this, I'll call it the magical transition speed, where you go from needing a positive G-force pushing you in towards the circle from the normal to something negative. And so you got to be strapped in, and if you had it over your shoulders, the negative would be pulling you, over your shoulders and keeping you in the cart. You would literally be in danger of falling out if you hadn't have those straps. So using those numbers, G is 9.8, the radius was the 7 meters, and then taking the square root of that, I get a transitional speed here of 8.28 meters per second. So that would be the minimum speed to stay in there without some kind of support system, so a seatbelt, holding on with your hands. Okay, now I think those are the easier ones, although I don't want to call those easy by any means. But now when we have something at an angle, let's do that free body diagram again. And we'll come back to question B, which, notice it says, what is the force that what is the force of the car seat on the child at point B? So a free body diagram, so here's the child, would still be gravity pulling it down, mg. And then the normal force would be perpendicular to the track, so that's pointing towards the center of the circle. And so I would have a normal force, something like this. And that's the main difference between how I would analyze this problem in part A, because here normal force is straight down, and then in part B I've got it angled at 30 degrees, Maybe I should point out that it's 30 degrees up here, but if you draw this vertical line, these are two parallel lines. This is a transient, alternate interior angles are equal, so I'm labeling that one here in my diagram as 30 degrees. Okay, so again, I think we've accomplished step 1 and step 2. Step 1 got a good physical picture of what's going on, and then step 2 here, I've got this free body diagram. Now, as you've heard me say many, many times, I think it is best to set up a grid so that one of your axes is in the direction that you know the acceleration, and since the center of the circle has to have an acceleration of v squared over r, I'm going to set up my axis towards the center of the circle. And I made a big deal out of that, and I remember some in the video lecture people asking me, and I said, you don't have to, but then you're going to get like sines and cosines, and then you got to have acceleration x, acceleration y, then you got to put those together, so you got some trig identities. And so it's your call if you don't want to turn your axis. I would say you're crazy. You got a lot of trig math to do now. Just turn your axes. All right, so I'm going to turn my axis, and so I'm going to kind of imagine now this is the x and this is the y, and so I rotated it, and I might even ask myself, you know, how much I rotated it. So I guess it'd be 60 degrees because I would have been horizontal, and I want to come all the way down until there's 30 from the vertical, so that means 60 from the horizontal. And so I can look at either the 60 or the 30. I'll probably focus more on the 30. Maybe I shouldn't even have drawn the 60 up there. But I did want to emphasize in green that I'm putting a grid on here because this step 3, as you know, is me saying add up all the forces in the x direction and set it equal to mass times acceleration in the x direction. And you set up all your forces in the y direction, and that would equal to mass times acceleration in the y direction. And for this problem, then, the acceleration, the x-axis is the center of the circle, and we know that it's v squared over r. And the way I did my axis, that would be a positive x-axis. So it's a positive v squared over r. So again, the whole point of this problem is that something going in a circle needs an acceleration. Its magnitude is v squared over r. Its direction is towards the center of the circle. Set up a grid, so one of your axes, either x or y or plus or minus, doesn't matter, any of those 4 combinations, set up one of them in that direction. And so this picture, I'm setting up the positive x-axis. So I put v squared over r in the x-axis, and I put a positive. Now, I must say, in the y direction, I'm not sure what it is. So I'm not sure if I can say anything about the y direction. So I'm kind of hoping here that, like this one here, where the x did me no good, that's the one that wasn't pointing towards the center of the circle, I'm hoping the y, the one that doesn't point towards the center of the circle, is useless, doesn't do me any good. I definitely would not say the acceleration is 0. So at least in part A, we could say 0 equals 0. That was pretty easy. Here, I don't know what the acceleration is because it would have some kind of speeding up effect. So it would have an acceleration in this y direction. But like all these problems, let's add them up. And I'm going to start with the normal force. And again, got to look at both the x and y component of each force. The normal force, the way I've set up my grid with a twist, all the normal force is in the x, so none of it is in the y. But I'll put a 0 to indicate that I am adding up all the forces and all the components. So there should be 4 terms because there's 2 forces, and each term would have an x and a y. Now, the normal is kind of boring because the y is 0 and the x is all of it. But the one that's a little more interesting here, once you twist your axis, is the gravitational force. Because remember, you can twist your axis, but you can't twist the direction of gravity. Gravity's still down. And so when you look at this, you can kind of see a triangle made out of here. maybe if I do it in blue, it'll stand out, but you would have a horizontal and a perpendicular piece. These two blue pieces, I'm saying, is equal to the mg. So the part that's on the x-axis is adjacent to the 30, so that would be cosine. So this should be mg cosine of 30. Whereas over here, this would be a magnitude of mg and sine of 30 and negative. So you can see in the y direction it doesn't come out to be 0, and so there is an acceleration, and we could even calculate what it is. But let's not do that since they don't ask that. What they ask is, what does this normal force have to be? So solving this, I would get normal force would have to be an mv squared over r minus an mg cosine 30. And now, once I get the formula, hopefully it kind of fits in with what we did back in part A. See, because part A was mv squared over r minus, and in this case, the full gravitational force, because a full gravitational force is pulling down towards the center of the circle. Whereas here, you would only want the amount pulling towards the center of the circle, which if this gravitational force is down, then this component, so with mg cosine of 30, is pulling towards the center of the circle. So that's why in part A, there is no sine or cosine. You might even say it's cosine of 0. And so now it's cosine of 30 degrees. So now I can put in the numbers. And so here is the 4. It is going a little faster, what I see up there, 10.5, so 10.5 squared. The radius is still 7. Again, 49.8 and cosine 30 degrees. So if I put in those numbers, I should get 40 times 10.5 squared divided by 7 minus then 40 times 9.8 times cosine of 30. And so now the normal force is 290, I'll call it 1 newtons. And so there's the answer to B. All right, hope that helped.